Daniel est pas dans le coin. Je le vois pas. Ouais, sinon, non, j'ai rien dit.
Français, mais Luc fera le séminaire en anglais. Mais comme on est en France, je vais quand même faire l'intro en français. Donc on a le plaisir d'accueillir Luc Deike. Moi, je connais Luc depuis longtemps puisque on s'est rencontrés en Nouvelle-Zélande sur un travail sur les vagues il y a longtemps. Après, Luc a fait une thèse à MSC avec Eric Falcon sur la turbulence d'ondes, en particulier la turbulence d'ondes capillaires. Après, Luc est allé à Scripps en postdoc avec Ken Melville, qui est était un grand spécialiste des vagues. Aussi le directeur de Scripps. Donc, Scripps, si vous ne connaissez pas, c'est un institut d'océanographie américain en Californie. Et après, Luc a eu un poste de assistant professor, c'est ça, assistant professeur à Princeton. Et depuis un certain temps, il est associate professeur à Princeton. Et voilà, et je vois la parole, Luc.
Merci beaucoup de l'invitation. Je vais switcher en anglais, mais si vous voulez me poser des questions en français ou en anglais, vous pourrez. Okay, so I'll be talking about sort of the overarching story of what we have been working in my group in the last 6 or 7 years. So I'll be talking about mass transfer at the ocean-atmosphere interface, the role of wave breaking, drops and bubbles, and kind of all the physics that I'll be describing or trying to describe in the talk is summarized in this picture that was taken from research platform Flip just after a relatively large breaking event. And what you can see are these large bubble plumes that are untrained below the water surface and that are going to modulate the fluxes of momentum and mass between the ocean and the atmosphere. So that's the idea. That's kind of the framework. We can look at more pictures or movies of these conditions at fairly high wind speed. So this is another picture that was taken during a winter storm in the North Atlantic in the Labrador Sea. This is like a nominal wind speed at 10-meter height of about 25 meters per second. That's kind of like when we start talking about tropical cyclone condition. It's that kind of wind speed. So it's very high wind speed. It's a few percent of the wind speed that are being observed on the ocean surface. And what you see in these conditions is that the surface is completely disturbed or distorted, that you have like these very large breaking events, these plumes of bubbles, these spumes of droplets that are transported in the air. And you can kind of easily picture that describing transfer of gas or heat or momentum in these conditions is going to be drastically different than if you have a very calm surface. And so that's going to be the motivation to try to develop an approach to describe the physics of this problem and down the line then improve the representation of these processes and these conditions in large-scale models. So why do we want to do that? There are a few key motivations from a climate perspective in terms of mass exchange at the ocean surface. One of them is gas exchange. So when you break the surface, you untrain bubbles, you trap these bubbles down in the water column, they can collapse. So you're going to significantly enhance the exchange of gas compared to an unbroken surface. It's going to be important for carbon uptake. It's going to be really crucial for oxygen exchange. So that's one reason to look at the problem, one reason to understand air entrainment, bubble population, and so on. The other motivation, which is the one I'll be developing today, is the emission of sea spray aerosols from bubble bursting and also from direct atomization. I'll focus on the bubble bursting part. So as most of you probably know in this lab, the bubble rises back to the surface. It spends some time at the surface. There is a film. The film shatters. It ejects drops in the air, and then you have a nice cavity collapse to emit jet drops. And then these drops can be transported in the atmosphere by the turbulent flow. They can evaporate, so they are gonna contribute to heat exchange and moisture exchange, and they are gonna leave aerosols. So they are gonna leave sea salt aerosols, biological particles, and that's gonna have a very large impact on atmospheric processes. It's gonna affect the radiative balance, and it's gonna affect cloud formation in marine environment. So you want to know the emission of sea spray aerosols for this kind of like reasons. It's not like a new question, right? It's an old problem. So you can ask like, okay, why do you want to like look at the mechanism? And there are a few very good reasons to look at the mechanism. The first one is the very large uncertainty in terms of what's called the sea spray emission function that are being used in large-scale model. So this is from a review that's a bit old, but the statement is still valid. So here you're plotting the production flux, so the number of aerosols at a given size as a function of size. And each curve is one parameterization that's been derived from either lab experiment or some theoretical argument or some field data. And so you have a countless number of studies that have done that, and they are a bit all over the place, right? They kind of all agree that you should have a peak around 100 nanometer. They kind of all agree that it should decay in some way, but then the shape of the distribution is very much uncertain. The magnitude of the distribution and these are log scales, so you have 2 orders of magnitude uncertainties at some size bin. So it gives you the idea that just looking at wind speed and just doing empirical measurements is not necessarily going to be enough. If you do the total budget of sea salt being emitted in the ocean and you integrate some of these curves, you end up with an uncertainty of about a factor 50 in mass of sea salt being emitted. Factor 50 is kind of a large number. If you have 50 times more or less sea salt particles in the air, you're going to reflect sunlight in a different way. So that's important to better constrain this thing. The other reason to look at the mechanism is that, so this is just plotting things for a given wind speed. This is plotting the same kind of quantities, so the normalized concentration as a function of temperature for a bunch of, again, field data or lab experiments. And then, again, you end up with a large variety of parameterization that you can pick from the literature. And you see that some curves go down by an order of magnitude when you go from very cold water to 20 degrees, and then some other go up by almost an order of magnitude. So if you are interested in doing climate modeling and you want to put sea spray parameterization in your climate model, and you want your parameterization to be temperature sensitive, because maybe that's what you see in some data, then if you pick something that decreases or something that increases and you run it forward for 100 years, you're going to get different results in terms of emissions of sea salt and then climate sensitivity to that parameter. So that's a good reason to look at the problem. And then the last point is that it's from an atmospheric chemistry point of view. Atmospheric chemists say that these aerosols are the chemical link between the ocean and in the atmosphere. And the droplets and the aerosols that are being formed are going to have different chemical properties and composition depending on the way they are being formed. So it's kind of like there is a micro layer near the ocean surface. It's assumed that there is a micro layer at the ocean surface. So you would assume that if you are producing drops from this film, then you're going to be more enriched in organics. If you're producing drop from the jetting process, you're going to be more sampling the bulk, and so you might be less enriched. So that's kind of like the reason to look at the problem. And so now the way we are going to look at this is by not considering the full problem at once, but breaking the problem into a set of simpler problems. And so I called this a multiscale approach, but there is no like small parameter in the multiscale approach. It's just like splitting the problem into 3 bunches of problems. I'm going to be talking about what's going to be my large scales, even if it's still small scale from an oceanic or atmospheric point of view. So I'm going to be talking about wave breaking statistics, So if you have a certain wind speed, what's the wave field, what's the wave braking statistics associated with it. And then I'm going to zoom on a single event, and I'm going to be describing the physics of a single braking event, how much air is being entrained, how much energy is being dissipated for a single braking event. What's the bubble size distribution? And then I'm going to be zooming in to the individual bubble processes, so the bursting problem, or if I was looking at the gas exchange problem, then the individual bubble dynamics. So that's kind of the outline of the talk. And I'm not going to do it linearly in scale. I'm actually going to start with the center, and then I'll go back to small and then large again. So I start with the physics of a single braking wave. So there has been like tremendous efforts to understand braking waves, and a lot of lab experiments were done. So this is like a set of images obtained in a wave tank, at Scripps. So you have a 30-meter long facility, about half a meter wide. You generate a focusing packet, so you send high frequency wave first, low frequency wave next. You tune the phase so that they all meet at the center of the tank, and so at the center of the tank you end up with a repetitive braking event. You always know where it's going to break. You can put your cameras, your instrument, and all of that, and study the braking event in that way. So Ken and others have done these experiments in the last 40 years, so you have lots of data on this. And what kind of comes out of it is that the two critical variables that control the braking event is going to be the speed of the wave, which is related to the wavelengths, and the slope of the braking, so the ratio of the amplitude of the wave over the wavelengths. So the higher the slope, the more air you're going to entrain, the more dissipation you're going to get. And so we're going to think about characterizing braking waves with these two parameters. So the way we did this was by doing simulations, so using Basilisk, working with Stefan, and the work was led by Wouter, who was a postdoc for a few years in Princeton and is now a faculty in Oxford. So you set up a Stokes wave. There is an old poster of the same simulation in the corridor. You let the wave move forward, and you create this kind of strong braking event. You entrain the tube of air that you see here. The tube of air collapses into a bunch of smaller bubbles. And so you can kind of compute everything you're interested in this simulation. And this was done like kind of at the technical point, right? It's using the adaptive mesh features, and it's using like up to a level of refinement of 11. So you're resolving like 3 orders of magnitude in scale, so that you can probe the size distribution of bubbles. And so the summary plot of this size distribution of bubbles is the following. And so on this graph, you have both lab experiment and simulation. And the x-axis is the size of the bubble divided by the so-called Hinze scale. The Hinze scale balances turbulence, so the deformation induced by turbulence and the restoring force of surface tension. And so at the Hinze scale, bubbles larger than the Hinze scales are going to tend to break. Bubbles smaller than the Hinze scale might not break due to the turbulent fluctuation. And so you see that if you look at bubbles larger than the Hinze scale, you have a certain distribution that follows more or less r minus 10 over 3. And if you look at sub-Hinze bubble, then most of the data lined up on a shallower slope. And so we wanted to understand this distribution. The minus 10 over 3 was explained in the literature by a turbulent cascade argument. So that's a paper from Garrett. And then the question was more about the understanding the sub-Hinze regime. And so we're going to do some simulation, but we also did some lab experiments. This was part of the PhD from Dan. And so what we did is we had a turbulent tank with turbulence created by an array of jets. And then at the center of the tank, we inject a large air cavity, which you saw here, getting completely fragmented by the turbulent flow. And so from these kinds of experiments, you can track down, you can develop algorithm to track down the bubble sizes as a function of time. That's what's illustrated in the insert. And then you can do these experiments for different cavity size. And so what you see is that if you start with a cavity size that's close to the Hindley scale, so that's going to be my dark greenish here, you're mostly producing bubbles around the Hindley scale, and then you have a few satellites down here. But if you increase the scale separation, so if you're starting with a cavity that's much larger than this stable scale, the Hindley scale, then you're creating a whole continuum of scales, and you actually recover this R-3 half that we were seeing in the breaking wave. You can do the same game in simulation. So you set up 3D periodic homogeneous and isotropic turbulence box. You inject a bubble at the center, and then you look at how it breaks. And so if you do something where you're just above the Hindley scale, just above critical condition, you get kind of this mild breakup, and you produce a few children. If you start with a much bigger bubble compared to the Hindley scale, then you get these very large deformation, the formation of these nice ligaments, and the production of many tiny bubbles. And so this was done a lot by Wouter and then Agenor, who is around here. And so we started like kind of picturing the process in the following way, which is that if you are in this range of my diagram, so bubbles close to the Hindley scale, you're just like locally producing smaller bubbles. If you're starting to have like a much larger bubble, then you are able to make kind of jumps and directly produce tiny bubbles. And so Agenor then analyzed all these events kind of individually. So you take each simulation that you have, and you go and look at each breakup event, and you see these like kind of long ligaments that are being formed. And what you can do with a lot of patience is to trace back every event as a binary process. And so you have the size of the parent and then the size of the two children. And you look at the time scale to form a children of size small delta. And that's what's plotted on this graph. And what you can see is that this time is always smaller than the turbulence time, which is the dotted line. And if you ensemble average your data, you're actually closely following the capillary time scale. So the formation of these small bubbles is actually controlled by the capillary time at the smaller scale. So the capillary time of the ligament that is being formed as you deform the bubble. So you end up with a kind of a picture of a two-step process that you deform the bubble in a time scale that's controlled by the turbulence. That's the eddy turnover time at the scale of the large bubble. At some point, you form these kinds of neck and ligament, and then these neck break into tiny bubbles in a time controlled by capillarity. And you can take this idea and write a population balance equation, and if you do that plus a couple of other assumptions, you end up recovering your R-3/2 scaling. Yes? Lequel? Celle-là? Oui, donc en fait, yeah, okay. So above, here you are at the Hindley scale, and so you're kind of expecting to recover the other scaling. Yeah. So that's why I'm kind of focusing on this part. So it's one of the, like, to obtain, and same, like if you look at these curves, then you don't get this scaling. So to get that, you need to start with a cavity that's significantly larger. And to get cleanly the -10/3, you need a really big volume because you need to inject continuously to like kind of maintain this cascade. It's like you make arguments that are kind of sinking in steady state, but it's really just transient all the time. So it's valid in a kind of short amount of time. It gives you the initial condition. It gives you like, okay, what's the population that's created? That's the population. Okay, so to summarize this part, you end up with this picture that either if you consider large cavity in a turbulent flow, or if you look at breaking wave, you have this population of bubbles that larger than the Hindley scale follows the turbulence cascade scaling, smaller than the Hindley scale, it follows this capillary scale. And so that was kind of like one step in the process, is that now we can think of the air entrainment and the bubble population and the breaking wave as something that is like well defined, right, well described, And so you can move on to now look at individual bubble, or move up and look at the statistics of breaking wave, knowing that for every breaking event, you're going to be able to assume this kind of population. So now I'm going to move to this part, to the part of the smaller scale, and discuss how the droplets are being formed from these bubbles. So a little bit of background. So there are a couple of processes that have been discussed in the literature to describe the emissions of these droplets. You have the idea that when you have bubbles, the film between the bubble and the air side rupture and then destabilize and produce droplets. These pictures are from Henri Lussier. And then you are left with a cavity underwater, and this cavity is going to collapse and form a jet, and the jet is then going to rupture and produce a bunch of droplets. This was done in this building during the thesis from Elisabeth Gabache with Thomas Hill. And the film drop process is going to be effective like for sizes around the millimeter. And the jet drop process is going to be effective for, like, I'm talking like kind of in water, for ratio of the bubble size to the viscocapillary length going in a certain range. So the two processes have a range of sizes where they are going to overlap, but they are not going to produce the same sizes of droplets. So that's kind of the idea. So again, you can do it experimentally. You can also do it numerically, especially for the jet drop. This is actually an old simulation. It was done with Jerez, but then with Alexis Bernier, we redid it with Basilisk. So you start with a cavity, you let it collapse. You have the capillary wave that nicely focuses towards the center of the center of the cavity, and then you form a nice upward jet, and the jet is going to destabilize and produce a bunch of drops. Okay. So you can do this for a wide range of conditions, which is what's summarized on this plot. And you can observe things. You can observe kind of a change in morphology of the jet. So the different colors correspond to different bubble size compared to the viscocapillary length. So that's the Laplace number going from about 1,000 to a larger number. When your Laplace number is around 1,000, you get this very thin jet that produces very small droplets that are very fast. And when you are at a much larger Laplace number, you have like more of a fatter jet with fewer droplets and smaller jet. And it gives you the range of productions of droplet, and in what air-water condition, it's going from about 10 micron to 2 millimeter. And so you can look at the sizes of the drop being produced. And so this plot shows the size of the drop, the size of the first drop divided by the viscocapillary length as a function of the size of the bubble divided by the viscocapillary length for lab and numerical data from our group, from Elisabeth's thesis experimentally, and from the group from J.C. Bird at BU. And so you get this very nice collapse of all the data that from the critical value that's around 1,000 in terms of the Laplace number, all the data collapse and can be described by scaling laws that were developed by either Gagnon-Carvo or Gordillo. But since they were fitted on the same data set, they are kind of indistinguishable. And so again, you can describe like the size of the drop as a function of the size of the bubble. So if you have followed what I've been talking about so far, I've been telling you what's going to be the size distribution of the bubble underwater. That's my red box. And then I have told you how you can retrieve and then kind of describe theoretically the size of the droplet as a function of the bubble. So if you take these two ideas and you convolute and you say, okay, each bubble is going to go at the surface and burst, you can like predict what's the size distribution of the drop for the corresponding process. You need to know something about the PDF of sizes, which you can again work on. So this we did for the jet drop during Alexis' thesis, and then other people did it for the film drop processes in Emmanuel Villermo's group, and then Xiaofei Wang group in Shanghai. So we're going to test these ideas again against a lab experiment that was designed to look at collective bubble bursting. So This was a project that has been going on for a while. In my group, it was initially worked out by Baptiste, who was a postdoc. He is now Maître de Conférence in Marseille. Megan is currently a grad student in the group, and Martin was a postdoc in the group. He's moving to Michigan at the end of the year. The idea is quite simple. You have a 0.5 meter tank. You create an array of bubbles of known sizes. You let them rise to the surface. You can activate turbulence or not underwater to break the bubble and have a polydispersed distribution. And then you can measure the droplets that are being generated. So if you have good eyes and the projector is good enough, you should see a droplet bouncing around on the upper side of the movie here. This is what it looks like if you look from the top. When you have a broad banded size distribution that looks like the one that I've been describing in the breaking wave, you see multiple sizes of bubble. They spend some time underwater, they pop. And so you can ask whether or not you're going to be able to describe the resulting drop size distribution from the ideas that I've been describing before. So we are kind of measuring everything we can in the experiment. So we measure the size, the surface size distribution. We have a combination of camera to be able to zoom down to 20 or 30 micron, and then also capture the ones that are around 10 millimeter. And since we have understood how to obtain a size distribution that's kind of comparable to what you have in the breaking wave, you can get that in this experiment too. And then we have a suite of instruments to measure the corresponding aerosols and droplets. So for the large drops, we're using either an holographic technique or shadowgraphy technique. And so we are getting liquid droplets from about 10 micron up to something like 500 microns. So all these drops are measured as they fly in the air. And then we have two other instruments that measure dry particles. So the way it works, you suck air out of the chamber, you dry the droplet, and then you measure the salt crystal that's left behind. And then you can, if you know the amount of salt that you have in the water, and you make the assumption that a single drop gives you a single salt crystal, then you can match the sizes of your dry element and the liquid element. I'm happy to talk whether or not it's a good approximation, but that's what everybody does, so we're doing it as well. So you end up with a very nice continuum of scales, right? You are measuring aerosols or droplets down to about 100 nanometers, and then up to 500 microns. And something that was already kind of remarkable and we were really happy about is that we're connecting the three measurements, right? There seems to be a continuum of scales. Like the distributions are not shifted vertically in a weird way. Okay, so now we're going to do some attribution game, right? You have knowledge from single bubble. If you take a bubble of this size, you can take the scaling laws from the literature to like say where it lands on the other graph, and you have the magnitude of the bubble size distribution. So you should be able to actually match this quantitatively. So that's what Megan has been working a lot on, and it's kind of coming together now. This is kind of a summary of the idea, right? So these are two examples of these distributions that we have been working with. This one has more bubbles, this one has less bubbles. Both distributions are very broad. And if you take the assumption that you're producing film droplets through a flapping mechanism in the orange range, so bubbles from about 80 microns to about 1 millimeter produce droplets in the sub-micron range, and you take the scaling relationship that are published in the literature, you can transform this into like the orange curve. And so you're describing nicely this peak in the data. And then the jet, if you say that jet drops are working like from anything around 20, 30 micron up to 2000 micron, and then you are creating this size distribution of droplet. And it can change conditions, and it kind of works as well. And we have other conditions where it works. Sometimes it doesn't work as well, but overall, you're always capturing this kind of peak by attribution to this range of bubbles. You're always capturing the larger droplets through the jetting mechanism. So you're kind of confirming something that was in some aspect of the literature, that jet drops are producing most of the supermicron sizes, while film drops are producing most of the submicron sizes. And so from this, you can kind of like conclude that if you want to know the size distribution of drops, if you have knowledge of the bubble size distribution at the surface and you combine with the knowledge of the emission mechanism, then you get a very reasonable result. Okay, so with this, I have described like kind of these two vignettes, right? So the breaking wave scale and then the droplet production scales at the bubble scale. Now I'm going to move back to larger scale and discuss like what you need to know, right? Is you need to know if you look at the patch of the ocean for a given wind speed condition, how many of these breaking events you have, right? I have hopefully convinced you that if you know how many breaking events you have, you're going to be able to integrate everything and produce your C spray emission function. So the waves at the ocean surface itself is going to be like described by a continuum of scales. So you're going to have a turbulent boundary layer that generates a wave. These waves are going to grow in wavelength and in height. So if you are like in a place with a mild wind, or if you have just started generating waves, you're going to have like these kind of patches of small capillary waves and small gravity waves. If you look at if you are in a like fully developed sea where you have very strong winds, you're going to get these kinds of pictures. So you're going to have scales from millimeter to hundreds of meters. The way it's characterized in the field is through the measurements of the wave spectrum. So it's like a turbulent spectrum, but for wave energy. This is a typical measurement done by LiDAR. So it was done in Ken's group, flying a LiDAR in an aircraft, and then you're measuring the patches of the ocean, and you compute the wave spectra. And so in this particular case, you have the peak of the spectra that's around the wavelengths of about 100 meters. And then you have two power laws that describe the wave spectra. One regime that's called the equilibrium, and then one regime that's called the saturation. And the saturation part is the part that's associated with breaking event. It's going to be wavelengths, anything from 10 meters to 1 meter. And so it's going to be associated with these kinds of strong breaking events or less strong breaking events that you can also measure through aircraft imagery. So this is like a camera that's on board that's looking down at the ocean surface, and so the image, right, is moving fast to the right because the aircraft is moving faster than the wave, and so you see this big breaking event that moves in the opposite direction. If you have these images, you can do PIV style analysis, so you can extract the length of breaking crest and the speed of the breaking crest, and you can construct statistics of the breaking crest. So this was done in the field, and so you can look at the data. What we did in the group, and that was part of Jarong's PhD, was to use the multi-layer formulation that Stefan developed to look at the breaking statistics from simulations. So here you're solving the Navier-Stokes equations discretized on a set of connected layers. And the beauty of this formalism is that you can recover the breaking dynamic that's kind of like models as shocked in the scheme. So what you see here is like a patch of your ocean, if you want. The box is maybe 200 meters by 200 meters if you want to put scales on it. And the red patches are these breaking events. That's the speed of the first layer. And so when it gets red, it means that it's close to the speed of the wave, and that corresponds to a breaking event. So you can set up these simulations with a realistic wave spectra. That's what's illustrated here. And then you can look at the breaking statistics that you recover by doing this. And so you get something like this for this metric, which is the distribution of lengths of breaking crest moving at a certain speed c. So you have a peak that's around a fraction of the speed of the peak of the spectra. And then you have a steep decay, which follows something like a c minus 6. And then the largest breaking event are something like with a speed a bit smaller than the peak of the spectra, which makes sense because this is the fastest waves you're going to have in the system. You can do this for a wide range of spectra. And so you can then study how your breaking statistic scales with the property of your initial spectra. So this is the mean square slope. It basically quantifies the strength of the wave field. You integrate the wave spectra, so you have it's a measure of the strength of the spectra. And so you see that if you increase this slope of the wave field, you are making more breaking events. That makes sense, right? More energy in the wave field, more breaking event. The shape of the breaking distribution is kind of always the same. And so you can then try to rescale this thing by proposing something that only depends on the mean square slope. And that's kind of promising because it tells you that while at the ocean surface, obviously the wave energy is driven by the wind input. What these simulations tells you is that the whole breaking statistics is controlled only by properties of the wave spectra. So if you measure the wave spectra, or if you model the wave spectra, which is much easier than modeling the breaking statistics, then you can retrieve the breaking statistics. So you can test this scaling, the scaling that Jarong proposed against field data. So all the red and orange curves are from Jarong's simulation, and then all the blue and gray data are from various field data. And depending on how optimistic you are, you can say that it's a great achievement, it's kind of collapsed, or you can be less convinced and say that there are still like a very wide range of uncertainty in this thing. It's really a measurement at sea that's not easy. So with this data set, you're not going to do better. With better data set, you might hope to like narrow it down. And side point, like the fact that some curves here go back up, it's not. It's because it was measured with infrared imagery, so you're actually measuring smaller scales than all the other curves which were using visible imagery, and so you have an artificial cutoff due to the visible imagery. So that's where we are. And so at this point, you can recombine all the scales, right? You can be happy with what you have learned for the statistics of breaking wave as a function of wind speed and wave statistics. You have a description of the air entrainment bubble statistics, and then you have a description of the associated emission of droplets. So you can do that. You can do that formally by integrating over all the breaking events. So that's the integration over lambda c. You integrate over all your bubbles, that's integrating over this quantity. And then you apply the production function that you have derived for individual event. And so at the end of the day, you end up with a C-spray emission function. So that's the same quantity that I showed initially. So that tells you, that allows you to quantify the size and the number of droplets or aerosol being emitted. So it looks something like this. So it's an example. So it's at this point all modeling for the same wind speed, but two different instants in a storm. You see that because you have information about the sea state, you generate some variability between the red and the blue prediction. And then all the little dotted line and dashed line are some of the predictions that are in the literature. The greenish, some of the empirical formulation that are in the literature. The greenish thing in the background is another one. And so you can conclude various things, right? You can have satisfaction that you are reproducing the main feature, right? The peak is at the right point, the order of magnitude is in the right point, the overall shape is reasonable. So it's not to say that like you're matching exactly, right? But it's to say that you're getting the right feeling, if you want, or features. You can also explain some of the variability that was observed in the empirical data set because you have the direct control of the waves. And you can also like kind of touch on the temperature idea because there is a very weak temperature dependency in our formulation. So it would suggest that you have to think about the data set that we're finding a strong temperature dependency. Okay, so then, so this was kind of like the whole physical construction. And then I do have still a few minutes, so okay. And so then the last step of all of this work is to go to the neighbors in the other building, or in my case, it's down, across the road, right, to go to the people that run climate models or ocean models or atmospheric models, and to give them these formulations that you hopefully are more physics-based, so you hope that they should kind of like improve something. And so we do that with Brandon Reichel and Fabien Porot that work at the NOAA GFDL Center. So you have, if you want to think globally, right, you're going to use, if you want to compute these emission functions globally, you're going to use products that are reanalysis for the wind speed. So it's based on observations, on satellite observation, and then modeling. And so it's all available, right? And so you can recreate the wind field at 10 meters over the last 50 years or so. So you have that. You can run operational wave models. So WaveWatch 3 is the one we used. It's developed by NOAA. It's also used, developed a lot by people at Ifremer. And so from these wind maps, you can create wave maps. Okay. So here you have, right, typical pictures of these things. You have strong winds in the higher latitude. Associated with strong winds, you have strong waves. Things like that. And then with the framework we talked about, from that we can then compute air entrainment, so you can have like an idea of your basically bubble population by associated your wave field with your air entrainment property. And then you can produce emission of sea salt. And so you get, so this is a global map. It kind of shows features that you're going to see in any of these sea spray emission function. You can compare what we get to existing formulations that are used by various modeling centers, and you can discuss like similarities and differences. So our formulation has a very weak temperature dependency, so it actually corresponds quite. If you look, so this is integrated with latitude. So the atmospheric scientists really love to do that. It's called a meridional profile. You integrate, you average over the longitude, so you have these profiles as a function of latitude. And so you see like strong emission at high latitude. Our work kind of closely matched another formulation, and it's quite different than a more recent one that had a very strong temperature sensitivity. And so then you can kind of like argue which one you should be using and think about that. So that's been kind of like the whole story map, like developing a multi-scale framework, looking at the detailed fluid mechanics at certain scales, looking at ways to integrate this information and then push this to large-scale models, and then you can apply these sorts of approach to other problems, right? We had a project on microplastic. We have worked on gas exchange. Yeah, thanks a lot.
Thank you very much, Luc, even more so with your voice. I hope it's not too painful, but thank you. Are there any questions?
Thank you, Luc, for absolutely great talk. Thank you very much. It makes me very happy to see that. I have one question. Why do you have such a close match with the gong data in the last slide?
Right. So what's really dominating here is the wind speed dependency. So gong is like something where you have a certain shape that's not too far from the shape I get with all my complicated things. So gong is like, I forgot which one it is, but it's one of the gray lines that's hidden. These things are in mass. So mass, you're taking mass below 10 micron, and you're dominated by the 1 to 10 micron aerosols, because that's what contributes most to mass. If you look at number, you would be dominated by here, but because you. And so what you see is you're like the shape of the profile completely depends on your wind speed scaling, and whether or not you have a temperature scaling. And gong doesn't have a temperature dependency. I have a very weak temperature dependency. So that's why you get very similar result. The other formulation have a very strong temperature sensitivity, and so you have warmer water near the equator, and so you end up with these like secondary bump in the tropics.
But these are other formulations, they are not measurements.
No. Well, it's tricky, right? So all the formulations of some form of fits on the measurement, but you have two ways to construct these parameterization empirically. One way was what people called the bubble method, which was you were doing some experiment in the lab, you were measuring some flux, and then you were taking white cap coverage, scaling with wind, you stuck the two together and you get the prediction. And that's how Gong was constructed, and that's kind of, it's a bit the same philosophy as what I did with maybe like more ingredients, but it's the same kinds of ideas. The other approach is to take data of aerosols measured in the field, usually from aircraft. So you're measuring anything from a few 100-meter high to kilometer or something like this. And you have a concentration there. And then from this concentration, you're backtracking emission. But you have to make assumptions about the vertical transport. And these assumptions are extremely crude. And so that's, to me, that's where the temperature sensitivity comes from. It's actually an interpretation of the data to the surface. But the temperature sensitivity probably comes from something in the vertical transport. Because if you have convection, the strength of your convection is going to depend on the sea surface temperature. And so.
Thank you for the talk. I'm an absolute newbie in bubbles, and my question might be evident or stupid. Do you have a dependency on parameters like local atmospheric pressure, or other more physical-chemical parameters like, I don't know, if you have a localized patch of pollution, does it change
right.
some parameters of your modeling?
Okay, yeah, it's a very good question. So I'll answer the first one. The answer is not too much, because if you are like, these processes are happening really at the surface, and the layer of air above the surface is always saturated in humidity. So you're always like between 80 to 90% humidity. And so you're not, the assumption has always been that you're not affected by the airflow above. You can like, you can talk about this one. We are seeing, like, we have a postdoc that visited, I think last week or something like this, that's doing experiments where he sees a clear effect of the flow of the airflow on the bubble lifetime. So maybe there is kind of an indirect effect through that. But my answer is to first order, given some of the other assumptions that we make and all of that, it's probably fine. The other question is really important. That was one of my points in the introduction about the like kind of chemical composition. We know that it's important because if you put surfactant in your tank, you're changing the bursting processes. But it's not been quantified in a way that's easily plugged into this framework. And you have absolutely no idea what's in the ocean in terms of chemical composition, associated surface tension, associated isotherm. So it's really hard to like link these things, so you can do a lab experiment and retrieve quantities and hope to say something. But there is really a gap in the knowledge that you have about surfactant and contamination in the ocean is extremely crude, and then you don't have a clear link in terms of modeling. It's kind of like, how do you, like, what's the right way to model this? And if you know this, then you can start telling people that make measurement, well, I really need to know this quantity. I don't know if you do lab experiment, but anyone that's measuring surface tension in the lab actually relies on gravity not moving. A ship is moving, so you can't measure surface tension. So you have like really basic things that. We're working with a geochemist in Princeton. He's taking samples, he's freezing the water at sea, and then he's bringing it to the shore. So we're hoping to do some experiment with this actual seawater. We're doing experiments with like adding stuff and seeing what's happening. But yeah, it's really tricky. And you have about kind of oil spills specifically. You have really incredible work from the group from Joe Katz and at Johns Hopkins, where they did work with actual crude oil and the actual chemicals that are poured in the ocean when there is an oil spill. And what he's seeing is that everything you're putting in the ocean goes back in the atmosphere through these processes. So if you're putting like a dirty chemical to break the oil because you don't want big oil patch, then you get it back as aerosol in the air.
Thanks a lot.
Maybe I have one on the experiment. You know, when you show the experiment, this one,
yeah,
and you show the the measured size distribution, you say you are happy because you are connecting the two distributions.
This one?
Or yeah. The one just before?
Ah, the one just before.
Yeah, and we see. Yeah, so it looks nice. So can you comment on the point in between?
Here?
No, the
or
big,
here.
I mean the patch where you have measurements just in the middle. Yeah.
Okay. It's two different instruments, and they somehow report the binning in a different way. So it's a defect of this plot. This one has been like kind of interpolated more. So it's more the way it was plotted than all that. So it's, I mean. You have really questions of statistical convergence of all these things, right? It's like you need to run the experiment long enough to actually capture enough droplet to actually have something reasonably converge. And depending on the bubble condition, you have more or less droplets, and so you have data sets where you're kind of at the edge statistically.
Another one. I have one on the numerics, so you
yes,
may say so when you show the distribution of bubbles, you show a nice convergence of to the -3Fs.
Yes.
On various using various
this one,
results. Yeah, this one. But you see that the DNS is actually seems to be different, right?
Which one? This one?
No,
yes, this one from Buddha. Yeah. Yes.
We know it's converged, right? Or we are confident it's converged.
It's pretty well converged, right? I mean, this you have overlap of the distribution like on this part, and so then these ones are the last points that you don't have the level 12, and
so you think eventually we should be able to.
Yeah, I mean, yes. So again, it's always the choice when you make the plot whether you keep where you cut, right? Like, and I don't know, I forgot how conservative we were when we did this plot, but maybe we were not.
I think we were pretty conservative.
I think we were pretty conservative, but like, again, if you take like 10 drop per diameter, 8 drop per diameter, 6 point per diameter, sorry, then you're getting a point or two more, and
Maybe one last comment is that a comment on, you said, okay, we get in the end we get the distribution of sea spray, right, which looks close or looks the same as the other parameterization. But even if you got the same one, I think it's very important because you got it in a different way, right? You have the arguments you are using are based on the microphysics, the detail, and then you end up with that. So even if the parameterization in the end gives the same result, the fact that it's derived differently is very important, right? It's
it's very strong, and I mean, what's important is that it's like you don't adjust the parameters at the end, right? You adjust at each scale. You describe a scaling, and so it might have a fitting parameter on a specific data set. But when you recombine everything, you're just like getting what you're getting from your nice integration.
It's
from
a
this
derivation
equation.
almost from first principle compared to something which is purely empirical.
Yeah.
That's a big difference. Okay, there is no other question. Thank you again.